We're all set to go. 3, 2, 1. Welcome from Castle Point. We got circuits again. All right, welcome everybody. I'm so glad you're here. This is the Exam 3 review, and I want to begin by, as always, thanking our colleague Andrew and his SIT colleagues for doing all of this for us. All right, now, my goal for tonight is to go over 5 problems, okay, which I think will be very representative of the exam. I also want to give you one hint that's also very representative. So that's my goal for tonight. All these exams are posted. Quiz 3 posted exams on the Canvas course website. My colleagues, I'd like to begin with Quiz 3 from the spring 2018. And this is version 1. Okay, so for the home audience, you can open up Quiz 3, Spring 2018, version 1. All right. Oh, perhaps before I even start going over, let me make sure we're all in sync. What's on the exam? 3 topics, okay? The first is nodal or mesh analysis using sinusoidal steady state. That's topic 1, and that's going to be the first question we're going to look at. Topic 2 is real and reactive power. Now, topic 3, for those of you in the room here, we still got Thursday's lecture. For you at home, I suspect you're watching this, of course, after the Thursday lecture. We're just going to have low-pass filters. Okay? We're not going to have high-pass filters on exam 3. I'm only going to start that on Thursday, and it's too much of a rush. So let me be very clear. For Chapter 6, it's just low-pass filters. And we got some very representative examples tonight of low-pass filters. So again, 3 topics: sinusoidal, nodal, and or mesh analysis, AC power, which is real and reactive power, and then low-pass filters. That's it. So let's begin. And my colleagues, I've met with a number of you about exam 1. And one thing I'm very impressed with is your ability to do nodal analysis. So here is a circuit, and it is now in sinusoidal steady state. Notice I've already done the conversions to phasor for you. Okay, I can't guarantee I'll do that, but I think I will because it just saves time. All right, so here is the circuit. I'll give you a moment to copy it. And Andrew, this is where you can cue the background music. A little light traveling music at this point would be nice. He's actually getting something. He's making a note of this. My good, Andrew, I'm only kidding. I'm giving you extra work. You don't have to do this. Andrew is so dedicated. Now, my colleagues, I sense all of you know how to do the first few lines of this problem. The question is, can you do the solving of it? And the only way to do that is practice. Now, I've posted a lot of exams with problems similar to this, so I would encourage you to practice this. This is one problem you should target getting full credit on. Okay. So, part A of the problem says, determine the steady state voltage V1. So I look up at the top, and here is V1. So I say, great, what we need to do is to write an equation for V1. And I'm going to go over here to this side of the board, and I'd like to do it with you to make sure you're all comfortable, and then we'll look at the solution. So I'm in that top node, V1. And what I get is V1 minus 5 at an angle of 0 degrees over, so V1 minus 5 at an angle of 0 degrees over 10. So hopefully now, if you got any questions, now's the time to stop me. And then plus, I have V1 over 20 minus J20. Okay, I can combine these two together. So it's V1 over 20 minus J20. So I get the 20 minus the J20. Now, I'm going to continue this on a lower line because my colleagues over here on the left won't be able to see it. So I'm just going to continue it down. Then it becomes plus. So now I can do the same thing here, my colleagues. V1 over 10 plus J10. Again, one of the major messages of Chapter 5 is we can now treat capacitors and inductors as resistors, except we got to keep track of the phase change. So now, if this was R1 and R2, all of you would see that this would be V1 over R1 plus R2. Same thing here, 10 plus J10. So the next term down here is V1 over 10 plus J10. All right, now I come over here and in part B of the problem, I ask for V out. For the time being, we can neglect V out. Okay, we can make believe it's not there. So what I now have is 10 minus J10 plus J10. Now, if I've done that right, that's what? 10 plus J10. Okay, so now this becomes V1 over 10, I think I said what, J10? And then all of this equals 0. My colleagues, you've done the electrical engineering part of the problem. You have now written the equation for V1. Now, did I do it right? V1 minus 5 at an angle of 10, 20. It looks like I've done it. Now, you can develop your own style as to how to solve this. Let me tell you my style. What I remember are two rules. So, Sam, when I want to divide or multiply, everything should be in phasor form. So I say, wait, what's phasor form? Phasor form is here, magnitude and an angle. You see that? When I want to divide or multiply, I'm going to have everything be in phasor form. That's easy. Now, if I get to the point in the problem, which I'm certain I will, where I have to add and subtract, I break things up into Cartesian coordinates. And I say, well, wait a minute, what's Cartesian coordinates? Cartesian coordinates are here. I know I've jumped ahead. I'll go back. The real minus or plus the imaginary. That's Cartesian. And it's very easy to add if everything is in Cartesian and also easy to subtract. So here's like the two guiding principles. If you want to multiply and divide, put everything in polar. If you have to add or subtract, put everything into Cartesian. And I think if you follow that with a little practice, you'll ace this. Now let me just go back and show you my approach as to how to do this. Okay? So the first line, I think we're all set on. Any questions on the first line? All right, excellent. Now, how did I get the second line? So here's what I do. I'd like to get rid of all the fractions. Right? My first goal is get rid of the fractions. So this one I can do in my head. V1 over 10, 0.1 V1. Then minus 5 over 10, 0.5, at an angle of 0. I got it. Now, notice here. I want to get rid of the fraction, but the denominator is Cartesian. Thomas, no good. I need it to be in polar form. So how do I get it in polar form? I keep the numerator where it is, and I say, this is 20 squared plus minus 20 squared square root, 28 and change. Then I say, okay, I have to get the arctan. Now, you can visualize this. 20 and then minus 20, right? Minus 20. So the angle is minus 45. And I do that for the for the third and the fourth terms. So now I have everything that needs to be divided in polar form. So I'm thinking, good. Yes? Exactly. In fact, why don't I show you? I'll show you on this board right here. Let me take the second term, right? The second term is V1 over 20 minus j20. And if you can do this term, you can do them all. So what I used to do when I was learning this is to draw this. Real, and then the imaginary, which is the j-axis. So draw this, 20, and then minus j20. So I know it goes down, okay? So this is 20, and this has a length of 20. So notice I don't include the j. J is just pointing. So now to get it into polar form, I have to know this length and this angle. So to get the length of the vector, it's 20 squared plus 20 squared square root. And the angle is the arctan, or the inverse tan, of opposite over adjacent. Now be careful, I should put the minus here. This is minus 20, because it's going down, 20. So you get the arctan of minus 1, which is minus 45. Did I do okay? Perfect, great. And my colleagues do the same for the last two terms. Okay? So now, what do? Let's get it all into getting rid. Nick, we're going to get rid of all the fractions. So I got the 0.1, perfect. Now, by the way, you might say, what happened to the minus 0.5? Look, I brought that over to the other side. If you look way at the end, it's brought over to the other side. And now, what do I have here? This is V1. Think of this as 1 times V1 at an angle of 0. So then I get 1 over. How do I divide vectors? Divide the numbers. So it's 1 over 28.284. And what we get is 0.0354. That's 1 over 28.284. Now, how do I get the angle? Oh, sorry. Yes, sir. Yes. Think of that. Think of this V1 as 1 times V1. And since there's no angle, it's at an angle of 0. Did I do okay? So now, help me out. Make sure I make sense. I now take the 1 divided by 28.284. And that gives me the 0.0354. Now I do the angles. When I divide, what do I do with the angles? Subtract. So there's an angle 0. Now be careful. Yeah, it's a double. Yeah, exactly. Be careful of the double negative, which you were. Perfect. So it's 0 minus a minus 45. I get the plus 45. And then I still got the V1. My colleague, how am I doing? All right, good. My colleagues, do the same for the next two. All right? So now, what I've done so far is I have succeeded in getting rid of all the fractions. But I now have another challenge, which we relish. Another challenge. I now have to add all of these. But they're all in polar form. So the easiest way, I think, to add vectors is to break them down into the real and imaginary components. Okay? So let's now move on to the next line. And I think once you get down to here, you're going to be able to take it on your own. Everyone with me down to here? All right, so what I now do, let me just scroll down just a little bit more so you can see the next line. Whoops, not that much. As you can see, I was running out of room here. Okay, so I'm thinking of my colleague who asked that great question in the back just a few moments ago. So I now want to add, and when you want to add, think Cartesian. So 0.1 times V1, that comes right down. And you might say, what happened to the V1? I just factored it out because all these terms have V1 in it. I then say, great, what's the next term? 0.0354, angle of 45. Tell you what, let me erase this here, and I'll do this for 1. And then the rest are all the same. So the angle is minus 45. So here, this is real, this is imaginary, and the angle is 45. That's the vector, minus 45. Oh, no, it's plus 45, right? Forgive me. I'm looking at the wrong term. I beg your pardon. I'm looking at, it's this term here, but the plus 45. Please forgive me. Plus 45. Sorry about that. Here we go. So now, this is real. This is the imaginary or the j-axis. And we have an angle of 45. So this is 45 degrees. Now, my colleagues, as I said in class, I think you can all do this better than me, because you have other courses where you have to do this. 0.0354, 0.0354. You now have to take the sine and the cosine of the angle, multiply by the hypotenuse, and you're going to now break this up into the real component here and the imaginary component here. Just be careful, when you get the imaginary component, you got to use j. So we now say excellent. So this becomes 0.0354 times cosine 45. That's the projection on the x-axis, or what we would call the real axis. You got to add the j, because now this is the projection on the imaginary axis. That's the sine. And my colleagues, do this for every term. Okay. So what you now get is we're going to be able to add this together very, very quickly. Before I go any further, Sam, help me out.
So for the second two terms, with v1 over like 114.14 times, and then there's a 2. Why is there no negative in the first term where you have negative 45? So like the term you just talked about, it's 0.0354 cosine of 40. Why isn't it cosine of negative 45?
Excellent. Sam, help me out. Sam's question is about the expansion here. Sam, let me slide this down so I can point to it a little better. Sam, the 0.0354 to 45, that's this term and that term. See? So I put the curly parentheses around that. Now we go to this one, 0.0707. That's 0.0707 cosine minus 45. And then it's minus j this, because it's the sine of 45. I could have made it the sine of minus 45.
Okay, I was just wondering where the minus went in that one. Like I looked at that one and I was like, well, that's positive.
Yeah. Sam, help me out. I don't mean to confuse people. This is how I see it. When I see the negative sign here, I know I'm going to have a negative j. So I just by instinct write it as negative j. However, I think mathematically I should have written it as plus j, but then made it the sine of minus 45. So whichever way you see it, as long as when we're done, whichever way we do it, we got a minus j because it's a minus angle. Sam, did I get your... We're clear? We're solid? I thought I saw a hand. Yes, sir. Yeah, if you see a shortcut, I'm afraid to say you can, because I think you're right. But what's happening here is, yeah, that sounds reasonable. The comment is, these two terms are identical. Can't you just multiply by 2? I think you're right. I'd ask you to double check it. I just don't want to say anything that's wrong on this video, because then I'll be in trouble. I think you're right. We can double check it in the next line. Good, thank you. I saw 2 other hands, and then I'll be right back. The last term, yes. I'm sorry. Yeah, I have to admit, probably not being very strict here. You're looking at this last term. 0.0707 minus 45. Cosine of a minus 45 is the same as cosine of 45. I should have put the minus here. And perhaps I should have made this plus and made this sine of minus 45. So, sorry, I don't mean to confuse. We're good, sir? No, that would give me, right, that would give me a positive j. right? See, the thing is, and my colleagues help me out, if it's a negative angle, right, like minus 45, let's be specific. Minus 45 is going to give me a minus j. Did I do okay, sir? I don't mean to confuse anyone, so please help me out. We're good. All right. So my colleagues, what we now do is just crank the numbers. So on the very next line, I'll just put the first equation here so you can see what happens. Notice, I did it term by term. So 0.1, 0.1. Now, Sam, 0.0354 times cosine 45. Turns out to be 0.025. J times that gives me this. So now, when all is said and done, I got a bunch of real terms and a bunch of imaginary terms, all captured right here. Now, this reinforces what we were saying earlier. The addition is now easy. The addition is easy. I sense a question from my colleague who saw me last week in my office. No, we're good? Okay. So now I now just have to add them. How do I add? Add the reals with the reals and the imaginaries with the imaginaries. So keep the j's together and the non-j terms together. And so I'm just going to add all this together. And I get this. I can't wait till the next tour, Grace. So my colleagues, I now have to solve for V1. Now, I suspect you know what I'm going to do next. I'm going to have V1 is 0.5 at an angle of 0 divided by the other side. But the other side is Cartesian. And if I want to divide, I need to convert this to polar. So look, you do a few of these problems, you'll get it. You just got to take a deep breath. It's a lot of conversions between polar and Cartesian, but you're going to get it. Yeah, I think I asked you to leave it in polar. My good man, I have a question for you. Forgive my eyesight. Yeah, are you the gentleman in the back who always... I love it. I got to get to know your name. Matt, my son's name. Oh, I should have known. Matt always gives me the thumbs up in the back. I'm down here desperate for feedback. And Matt, you just don't go. You go with, oh, Matt, I love it. Matt, I love it. Thank you, Matt. I really mean it. It brings a little energy. Thank you, buddy. Okay, so what I now do in anticipation of having to do a division, I convert this to polar form. And my colleagues, how do I do this? I take the square root of each, I square each, add them together, get the square root. Now, how do I get the angle? Now, you can draw it out or you can visualize it. There's a real part, then there's the j part that goes down. So it's the arctan. How did I get minus 18.43? And my good colleague is here in the front with her calculator. You can help me out. What I took was the arctan of minus 0.075 divided by 0.225, and to two decimal places, you should roughly have minus 18.43. Now it's done. It's just about over. And V1 is this. And then how do I divide? You divide the numbers, subtract the angles. Thomas is with me. And that's it. And in the problem statement, I said leave it in polar form. That's it. Part A is done. That's the biggest part of the problem. So my colleagues, I've told you all my secrets. The only advice is don't just look at it and say you can do it. Practice it. Okay? And you'll get the hang of it. You'll see, as you were saying, it's back and forth. Back and forth, whatever is needed, and you're going to get it. Now, part B. Oh, is there any questions? All right, part B. Oh, by the way, one thing I noticed, you might notice this also. You know, 2 or 3 decimal places is fine. I always write a note to the TAs because there's so many conversions back and forth. we're going to be a little bit off. I tell them, don't take off points for rounding. Okay, so don't let that be of concern to you. All right, go to at least 2 places, maybe 3, and that's it. All right, now determine part B, determine V out. Determine V out. Now let's go back to the circuit. V out was here. Now here's what I'm hoping everyone knows. We just determined V1. That's the voltage from the top to the bottom. I want the voltage just across this inductor. I'm hoping you all say voltage division. All right? And let's not even look at the answer yet. Let's see if we agree what the term should be. So, V, I call it V2 or V out? V out. V out. Now, think of this as, R3 over R1 plus R2 plus R3. That's what's happening here. So you're going to get J20. Okay, so J20, and I'll write it out so everyone can see it. So it's 10 minus J10, 10 minus J10, and then there's another term which is the J20. And all of this is times V1, which we got in part A. And that's it. Now, I suspect if you can solve part 1 with the math, part A, part B is a piece of cake. There you go. It's like 3 lines. Again, how did I do it? Notice I have Cartesian in the denominator. Convert it to polar. Now I have three polar terms. Easy. How do I multiply vectors? Multiply the numbers, add the angles. Then divide it. So I then divide it by this and then subtract that angle. And there you go. That's it. Done. Problem 1, over with. Nodal analysis for sinusoidal steady state. Are we all solid? You think you can knock this out of the park, as they say? You got it? I love it, Matt. I love it. All right. I heard someone say they missed something. Can I scroll up? Oh, you have to be, it's a classic. It only happens a few times every class, and I have to earn it. He just doesn't do it. He just doesn't do it willy-nilly. I have to earn it. Oh, yeah, it has to come natural. This is all we've scripted this for the last 11 weeks. All right. All right, so that's it. All right, now, absolutely. Good? Up a little. Andrew, how you doing back there? Are we talking the great American classic here or what? Are we talking like 2 thumbs up here? All right. All right, now, the next problem, before you write it, I'll give you time to write it. Can I just say something first? This is the hint I want to give you, okay? If you go back over my exams, all of my power problems are this, right? They're all the same, just different numbers, right? So I'm thinking to jazz it up a little bit. But wait a minute, you might say, wait, why now? Why not do it next semester? You don't have to jazz it up for us, please. We like traditional, all right? I tell you, if I were to jazz it up, here's what I would do. When does the homework due? Thursday? I'm going to be posting solutions. There's 2 homework problems. One with a current source in parallel with an RLC, and the other is a voltage source in parallel with an RLC. I would know how to do those 2 problems. Okay? So, Thomas, I see a question. Let me just draw this, Thomas. I'm working from memory, Thomas. I thought, oh, they did. I beg your pardon then, Thomas. Okay, Thomas, good. So Thomas, the two problems I'm thinking of, there was an R, L. Order doesn't matter. No, I think we're good. Tell me if I'm wrong. There was one problem like this, right? And Thomas, there was one problem like this, right? R. Yes. Right? My colleagues, I'll be posting the solutions for these. And I think, Thomas, help me out. This asks for the real and reactive power, right? So the real power only goes to the R. Now notice, it's in parallel, so you know V. So it's V squared over R, or to be more precise, VRMS squared over R. And then you do the same thing here for the reactances. Now, Thomas, here, I would find the current. If they're in series, find the current. And then from the current, you would then say I squared R, but be careful, it's not I squared R, it's IRMS squared R. And then IRMS squared times the reactance of the inductance, and IRMS squared times the reactance of the capacitor. So my colleagues, I want to be totally open, so there's no tricks. It's Thanksgiving. I don't want you going home feeling bummed out. I want you to go home and say, you know, I think that there's one course that I love, Mom and Dad and Aunt and Uncle and Uncle Harry. It's the circuits course. Oh, I want to tell you about real and reactive power. Have some turkey. No, I want to talk to you about real and reactive power. All right? So it's either going to be a problem like this or a problem like one of these. That's it. Okay? I don't know which one yet. I haven't made it up. Okay? So let's do this one, and I'm posting the homework solutions for these. So this is exactly out of the book. I just changed the numbers. I probably added a few more circuit elements too. So I tell you V1, and I tell you I. Oh no, do I tell you I? No, I don't, but that's okay. Okay, I don't tell you I. And when I tell you V1, determine the total real power delivered by the source. Now, there's a couple of ways of solving this. What I decided to do was to determine the current I. Now, I showed the direction of the current I going this way. So in this case, it's going to be 50 minus 0 minus V1. V1 is given. Divided by 50. Now, let me notice it again. I know we're so used to, here, let me slide this down. I know we're so used to saying V1 minus this over 50. But to make the problem actually easier, I show the current going this way. So if the current is going this way, it's 50 minus V1 over 50. 50 at an angle of 0 minus V1 over 50. That's what I wrote. And I write that, and I get this. So see, my colleague, help me out. 50 into this is 1 at an angle of 0. And then minus, then 27.8 over 50 is 0.55, and the angle is 3.91. How are we doing? Okay. Now, I want to subtract, but they're both in polar form. Yes, sir? Sure. So the equation here, okay, good. So I wanted to make sure we used a good direction of current that would work out. So I defined the current in this direction. Now, the current flows from the higher potential to the lower. So since the current is flowing this way, it's 50 minus V1 over the 50 ohms. That's it. So let me slide down. Did we do okay? Did I get it? And I gave you V1 so you didn't have to redo nodal and figure it out. That was problem 1. I now gave you the V1 to make life simple here. So what I get is 50 minus V1 over the 50 ohms. And you might think this is confusing, so help me out. 50 at an angle of 0 divided by 50 is 1 at an angle of 0. And then minus 27.8 over 50 is 0.55, and the angle is 3.91 degrees. Now, these are both in polar form. I want to subtract, so what I do is I convert to Cartesian. 1 at an angle of 0 is 1. Don't let that confuse you. 1 at an angle of 0 is 1. Real axes only, no imaginary part. Now, minus 0.5573 at an angle of 3.91. Draw that vector, use sine and cosine, and break it up into its parts. That then gives me this. So what I then get is 1 minus 0.5560 minus this j here, which gives me this. And looking ahead, I see that I have to divide it. So I'm going to convert it to polar, and that's polar version for I. We now have I. How did I do? Oh, Thomas.
What is this question asking?
For real power delivered by the source. And I know people are still writing. I'll be right back. Thomas, I'm given the voltage. If I knew the current, I could calculate the real power. Now let me slide down. Can I help? I'd love to help. You're not bothering me.
How do you get from like J20 to 20 at an angle of 90?
Oh, this is a good question. My colleagues, while you're copying, a side discussion. So the question is, was that in this problem or the previous problem? Okay, in the previous problem, there was a J20. Okay, and I wrote that with an angle. So here, the key to answering your question is to visualize this. So help me out. Remember, real J. So just think of J as a pointing vector for now. So how would I draw a vector points in the J direction whose length is 20? It would be this. And the angle is always measured with respect to the positive real. So it turns out that J20 is exactly equivalent to 20 at an angle 90. It's getting late. Okay. Did I get it? I want you to be solid. All right. You're here. I want everyone to whack, make it easy for the TAs to grade. All right. We're all good? Now, how do I calculate the real power? Do you have to memorize this formula? No. You'd be a better person if you did, but you don't have to. You don't have to memorize this because it's on the formula sheet. Oh, what's on the formula sheet, Professor? Exams are posted. You can look at and see for yourself. All the formulas I think you need are on the formula sheet. So now, remember, now please don't get this wrong. I want no one to get this wrong. IRMS is the peak divided by root 2. VRMS, the peak divided by root 2. Now, cosine theta. What's theta? It's on the formula sheet. Theta sub V minus theta sub I. That's my way of telling you. It's the angle of the voltage minus the angle of the current. Okay? And you now get the answer. Thomas, if I remember correctly, version 2 of this exam, if I remember correctly, is the same circuit, except in that case, part A was calculate the reactive power. So if you wanted to look at versions 1 and 2, you get the complete problem. Okay. We're good? How am I doing with the numbers? Good. All right. Box seats, how we doing? My colleague, Mr. NASA, who's now switched to rowing boats. Okay. Say it again. Because the angle of the current must have been negative. Right? So it's the angle of the voltage minus the angle of the current. We're good? All right. Now, my colleagues, part B and part C, and then we're done. Part B, determine the reactive power for the 75 ohm inductor. Now, before you start writing, let me say a few words. I have a question first.
For part A, for the real power, do you not have to account for power through the two resistors in the other branches?
Here's what you can do. Help me out. The question is, don't I have to account for the resistance and the real power there? Here's a very interesting observation. This source is giving away real power. That's what I asked in part A. But where does it go? R2 and R3. Yes. So what you could do, not that I would recommend it unless you got nothing else to do tonight. What you could do, this would actually be fun. You could do voltage division here. R2 over R2 plus J75 times V1. You get the voltage across R2. You can then figure out and do the same thing here. It should add up. We're good? All right, good. Now, part B. Okay, let me just read it. Then I want to go back. Part B is the 75 ohm inductor. Now, you asked your question at a wonderful time. My colleagues, I now ask for the reactive power in and out of this inductor. There's two ways to do it. There's the easy way and there's the challenging way, okay? The challenging way is to say, well, you know what? I take that back. I shouldn't say challenging. I think it's easier one way, but I did it both ways, and they're not that different. Here's the deal. I need either the current or the voltage for this inductor. Now, I take back my comment that one is easier than the other. It's which way you see best. Here, I give you V1. Now, you'll see I have this written up. How do I get the current? V1 over 100 plus J75. I get the current. Then how do I get the power? IRMS squared times 75. Perfect. Now, some of you say, no, I want to get the voltage. So it's J75 over 100 plus J75 times V1. That now gives you the voltage. And then you get VRMS squared over the 75. I did it both ways. Okay? So whichever way you see is the way to do it. So now let's look at here. Oh, I guess I didn't do the voltage division. I must have been tired. I'll leave it up to you to do it by voltage division, okay? But here is the current way. If you look at the circuit that you've drawn, how do I get the current through the inductor? It's V, think of V equals IR, right? Except now it's V equals IZ, where Z is the impedance. So I say I is V over the impedance. Okay? And the impedance in that loop is 100 plus J75. Boom. I get I. And then I say IRMS squared times the reactance. Remember, don't put J in this formula. It's just the numerical and the sign. So it's plus 75. And I get 1.86 VARs. You can call them watts. Now, there are some exams, I think in the fall of the previous year. I did do it both ways, but I was actually tired. I guess I didn't do it. You could do voltage division and get the same answer. My colleague, let me just write out voltage division because I sense you might want to do it. You never know. You might want to do it. Okay. Okay. Now, I don't have the circuit in front of me. The inductor was what? J75? So the V across the inductor is J75. And what was the resistor? 100? So my colleagues, help me out. Is it 100 then plus J75, right? And then times V1. You know what V1 is. You can now calculate this, and you'll get an answer for VL. Now, how do I get the reactive power? The Q for the inductor is now V RMS squared over 75. The J we don't need, right? We just go with this. Remember, we didn't use J here. It's very important. There's no J. However, if this was a capacitor, Thomas, I think that's in part 2, we would need the negative sign, right? So take the sign and the number, leave the J. Take the cannoli, leave the gun. All right. Are we good? Matt, I love it. You missed it again. Another classic. All right. Now, determine the real power to R3. Now, I know you want to copy this. Let me just go back to the circuit, just so we all know what we're now getting. Okay, R3 is here. Now, again, you could do it by voltage division. I did it by the current. So what you'll notice is V1 divided by 100 minus J25, minus J25. And that's what's there. Sir? Right, you're saying we know the current through the middle branch and we figured out I. Can I then can I use like a nodal analysis to get, yes, you can. You know what it is? I just find it easier this way. Maybe it's me. Subtracting, if I'm both in polar form, I think there's an extra step there. Okay. You know what I mean? But this falls out nice. But absolutely, the answer to your question is, if you do nodal analysis, that's another way to determine the I through the resistor. Because we know the I through the inductor, and we know the I through the source, so you could do that. I prefer this way. I think it's easier, but all right. Now, the only thing I want to give you the heads up on, and I'll come back to this. I know people are still writing. I want to give you the heads up. If this was an inductor, it's plus 75, which it is. If this was a capacitor, you'd have to have a minus sign here. I want to make sure of that, right? The reactive power for a capacitor is minus. That's our way of keeping track of the phase change between the inductor and the capacitor. If you look at, as I was telling Thomas, as Thomas and I were discussing, if you look at version 2 of this exam, you'll see that. All right, we've now done 2 problems. The only topic that's left is filters. That's it. So far, so good? Can I help? Oh, I never caught that. Good man. That's supposed to be P. I wrote R. Probably got a haircut the day before, too. Okay. You're absolutely right. Good man. No one's noticed that before. Kudos. P equals IRMS squared times R. You know you got it when you're catching mistakes like that. I'm proud of you. Way to go. Good man. All right. Anything else? All right. Let's do a low-pass filter. Now, yes, same exam. Just still from the same exam. My colleagues, I selected 3 low-pass filter examples. So you get the full array of what I could ask you. You don't have to stay for all 3. You can watch it on the recording. But let me start out. We're still on the same exam. Okay? So, and by the way, for those of you here tonight, we have like a couple more slides in the lecture to finish low-pass filters. So you're actually getting a preview of Thursday's lecture. Okay? So I say, I give you this transfer function, and I give you that break frequency. And I tell you, this is the input. Get the output. Okay? Now, I think you can do this. What you have to know is the concept of a transfer function. The transfer function is the output over the input. I give you it. I tell you the input. So you know 2 of the 3 things. And I ask you for the output. So let's go through it. So you might remember me saying a filter changes 2 things: the magnitude and the phase. So what you have to do is, first of all, get the magnitude of the transfer function. Now, please stop me if I'm not connecting. I go up to the transfer function, and the magnitude here, when you're in the complex plane, refers to the length of the vector. That's what I'm asking. So what's the length of the numerator? 1. What's the length of the denominator? I'm thinking of my good colleague here. So it's 1, and then there's a vector pointing in the j direction, right? So let me just draw that, my colleague. I know you know this, but let's do this together. This is real, imaginary. If I look at the denominator, the real part is 1. And then pointing in the j direction is f over fb. Now, I bet you everyone in this room can now find the length of that vector using the Pythagorean theorem. And by using the arctan, find the angle. So the length of the vector, the magnitude, is this. Now, I give you the formula for the break frequency, 1 over 2 pi RC. I give you that. And I tell you the value of R and C. So next thing I do is plug in, and I get right around 2274, give or take a little bit. Now, this is a low-pass filter. So physically, I want you to know physically what this means. Frequencies below 2274 make it through. Frequencies above start getting attenuated. So now we're all set. And I look up here. Be careful. Cosine 2 pi ft. F is 2500. So here's what I'm thinking, Matt. The input has a peak of 18.5 volts, but the frequency is 2500. The break frequency is a little less than 2300. I'm putting in a frequency above the break. I'm not getting out 18.5 volts. I'm getting out something less. I'm letting frequencies below 2200 and something through. Above, I'm going to try to get you out of there. Now, if it was a perfect filter, you get nothing out, but I don't know how to build a perfect filter. So I'm expecting a number to be less than 18.5. Whoops. How am I doing so far on this? Okay. So I now say, how do I get the angle? Okay. Now, my colleagues, let me go through this. Make sure I want you to get this. I'm thinking of my colleague who's asked a lot of great questions tonight. So this is like related to one of your earlier questions. I give you in the problem that h of f is 1 over, what was it, 1 plus j f over fb. Now, we got the magnitude. Now I have to get the angle. How do I get the angle? So the angle of h of f is the angle of the numerator. 1 on the real axis. Angle is 0. And you can't forget that. You got to write it down as 0. And then I subtract the angle of the bottom. Now, remember what I drew before? The 1 and then the j, f over fb. How do I get that angle? Arctan. So it's 1 minus the inverse tan of f over fb. So that's why I write here that this is the angle. Now, the break frequency, that's 1 over 2 pi RC. I calculated that. What's f? The frequency of the input. Let me say that again. I don't want you to get confused. F is the input frequency. F sub b is the break. That's 1 over 2 pi RC. So I think I have everything done. So what do I now do? The magnitude of h of f, right? Just look at this formula right here, is 1 over the square root of 1 plus f, the input frequency, 2500, divided by the break frequency, which we calculated. Oh, here it is. 1 over 2 pi RC squared. And what I get for the magnitude is 0.673. Let me pause. How am I doing? Good. All right. Good. Good man. Sam, help me out.
Why isn't the tangent of f divided by fb and not fb divided by f?
It's a TOA, right? Opposite over adjacent. So it's the j is f over fb. So Sam, help me out. Real, imaginary. It's 1, right? This is the 1. Now, j, we're given that it's f over fb. Sam, did I get it? All right. So, now, how do I figure out the phase angle? Okay, you're going to see it. I'm going to use that second formula right above the dotted line. The phase angle is minus the arctan of f over fb. F is the input frequency. F sub b is the break. And I get minus 47.7. Now, we're up to the final step. You've done all the hard work. Now, we're cruising home. There we go. V out, well, what's H? H is V out over V in. So what's V out? H times V in. We just calculated H, right? 0.673 at an angle of minus 47.7. Now, let's go back and look at V in. Make sure we all get this. V in is here. Now, how do I write this in vector form? 18.5. Angle of minus 12. That's it. Don't make it any more complicated. 18.5 at an angle, of minus 12. And then how do I multiply vectors? Multiply the numbers, add the angles, I get this. And now for this problem, and I remember Dylan asking this question. For this problem, I am probably going to ask you to get it back as a cosine. So how do I do that? That's the peak, that's the angle, and the frequency does not change. So 12.45 cosine 2 pi f, 2 pi ft, f still 2,500, minus 59.7. Done. Sir.
So when dealing with the form of the final answer or being in terms of the trigonometric measurements, the omega term will always be 2 pi ft, right?
Correct. Omega is 2 pi f. And in chapter 6, when we're dealing with filters, we work with f. So when we saw the input signal, it was 2 pi ft. So we focused on the f.
So if this were on the test, then you just had a number times pi that could divide by 2.
Right. If I don't think I would intentionally do that, but suppose by accident I did. So you're saying, let me write this down. Cosine 2 pi ft plus theta. That can also be written as cosine of omega t plus theta. Is that your point so far, my colleague? All right, so suppose I wrote it as cosine of 1,000 t plus theta. Is that what am I doing this wrong? Oh, yes. So we avoid having, yes. So what would I write it? This would be 1,000 pi t. Is that your question? Right. Thank you for the assist. So here's what I would say, my colleague. 1,000 pi equals 2 pi f. So then you get the pi's cancel. F is now 500. Got it. Thank you. All right. We're done. We're done with this. All right. We're all good? My colleagues, I want to be very clear on this because I don't want to get emails Monday morning at 1 a.m. Part B of this problem, not on exam 3. Thomas, what did I say? Not on exam 3. Part A. I don't even see it, Dylan. Part B, no, because Part B is a high-pass filter, right? No high-pass filters, all right? So Part A, low-pass, yes. Part B, high-pass, no. All right. Now, you don't have to stay, but I have 2 short filter problems I want to run through so you get the whole gamut, all right? If you need to leave, that's fine, but I got 2 more problems. Andrew, you still up for this? All right, my colleagues, we now go to quiz 3, fall 2017. Quiz 3, fall 2017. Version 1, thank you for asking. Quiz 3, fall 2017, version 1. Now here I give you a circuit. So here I give you a circuit. Oh, sorry? This is fall 2017, quiz 3, version 1. So now I give you part A. I give you a circuit now, not the transfer function. I give you a circuit. So I say, Determine an expression for h of f. All right. Now, this is what we did in class on Monday. I don't give you the transfer function. I give you the circuit. So use voltage division. Okay? Use voltage division. So V out is across the capacitor. Now, my colleagues, the reactance of a capacitor is actually easier to write it in this chapter as 1 over J 2 pi Fc. Now, as I've often said, if this was chapter 2, and that was R1, and that was R2, and I asked you for the voltage across R2, you'd all see it. It's voltage division. So what I want to write now is R2 over R1 plus R2, except this is a capacitor. So here's what we did Monday in class. V out is 1 over J 2 pi Fc. That's like the R2. Divided by 1 over J 2 pi Fc plus R. And all of this is times V in. I think you're all doing great. I really do. You're all doing great. No, you're doing great. Your dedication, I love to see it. I really do. Thank you. Now, I don't like the 1 over and the 1 over. So, first thing is I divide both sides by V in. So I get V out over V in. And now, I'm going to multiply top and bottom by J 2 pi Fc. So I multiply the top by J 2 pi Fc, I get 1. Am I doing okay? I now multiply the bottom, so I get 1 plus J 2 pi FRC. And now, to stay on this side of the board, I can take this last equation and write it as h of f equals 1 over 1 plus j f over fb. Can anyone tell me by looking at the bottom equation and the top equation what f sub b is? Right. F sub b is 1 over 2 pi RC. Okay, let me now slide down. And that's it. That's the answer to part A. We have a part B that I want to go through just to make sure you get it. And we have one other small problem after this, and then we're done. Sir? Yes, I'm going to skip that part. You don't have to know this for the exam, but you'll see the latter parts of this problem deal with the high pass filter, which we're not going to have. We're all good? We're good. You're helping each other out. You're good? Okay. Now, part B. My colleagues, this is just like the other part now that we had about 10 minutes ago. I now give you V in. I give you the values of R and C. So let's go through this quickly just to make sure you got it. Okay? So I say, all right, what's FB? 1 over 2 pi RC. I give you R, I give you C. Plug it in, I get a break frequency of around 277 hertz. Now, this is a low-pass filter. Below 277, I'm in. Above 277, I'm on shaky ground. I'm going to come out smaller. They're going to squeeze me. So now, what do I have to do? I have to calculate the magnitude of the transfer function and the phase of the transfer function. So here, this is what I need you to know. Can you get from here to here? Length of the vector, 1. Length of the vector, Pythagorean theorem. Plug in the numbers. The magnitude is 0.357. Now notice, what's F? And I'm reminded of my colleague. I don't know, did he? Oh, he's still there. Couldn't see you for a moment, sir. 2 pi ft. So F is 725. Now notice, my break is around 277. I'm really far up. So it turns out when you go through the math, I'm only going to get out about 36% of this signal. I'm going to lose a lot of it. So F is the frequency of the input, 725. What's F sub B? Sam knows. That's the break. So does Nick. So now the next step is, can you go from here to the angle? I think it's 0 minus the arctan of F over FB. So I say, all right, that's this. Now, my colleagues, you do a couple of these, you got it. I want you to leave here Thanksgiving and say, wow, I can't wait to get back to circuits. All right. So now, what you got is the magnitude and the phase. This is easy. What's V out? Multiply V in times the transfer function. What's V in? Oh, let me scroll up before we look at the answer. V in. My good man, this should be an angle of, a length 3.7, angle 52. That's it. Don't make it harder. Don't make it harder. That's it. So now we got 3.7 and an angle of 52. That's right here. Multiplied by the transfer function. And we get this. Now, last step. Thinking of my colleague back here who asked a great question about omega. Going from here to the cosine, hopefully no trouble. That's the peak. Cosine 2 pi f, as we know, f stays the same. 2 pi ft minus the angle. Now, a little footnote, you don't have to know this, but what the heck, you're a captive audience for the next 30 seconds. Do I have to know, is f always the same? It is if you're looking at what are called linear filters. For electrical engineers with us, there are things called nonlinear filters. And those frequencies change. But in this class, in this course, we're just dealing with linear. So we're not going to worry about frequency changes. So the heck with that. So the frequency always stays the same for our purposes here. How do we do? Sir? Yes. Question is, how do I get the angle of h of f? Are you good? I'll do it right here. Are you good in getting the transfer function? That wasn't very convincing. 1 over 1 plus j f over fb, you're good with that? Okay, then the rest is easy. You're 95% of the way there. So the angle of h of f is the angle of the numerator. Now the numerator, here, just draw it. Real, imaginary. It's 1 at an angle of 0. So the angle of the numerator is 0. Now, what's the angle of the denominator? Well, it's 1, and then in the j direction, it's f over FB. So here is the vector. This is the angle. So I want the arctan, the inverse tan of opposite over adjacent, but the adjacent's 1. So this becomes minus. Why minus? Because it's numerator and denominator. I always subtract the angles. So it's minus, and then the arctan of minus 1 of opposite over adjacent, which is just F over FB over 1, but we can neglect the 1. How do we do? My colleagues, how do we do? Matt.
So the break frequency for every single problem we've done so far has always been 1 over 2 pi RC. Is that consistent, or is that just...
That's consistent. Now, Matt, this won't surprise you. Suppose. And my colleagues, you'll see this in the lecture on Thursday. Just for the fun of it, Matt. Plus and minus V in. L R plus and minus V out. Solve it the same way. Voltage division. So what's V out? V out is R over R plus J 2 pi FL times V in. How am I doing, Matt? Now, let me write this over here. I don't want to write too low, Matt. Matt, you can probably guess where I'm going here. So, Matt, make sure I don't make a mistake. H of F is V out over V in, right? I'm running out of room, but this becomes R over R plus, was it J 2 pi FL, right? Now, every problem we've had tonight had a 1 in the numerator. So what do? Divide by R, top and bottom. So I divide the top by R, I get 1. I divide the denominator by R, I get 1 plus, here it comes, Matt, J 2 pi F L over R. Now, this can be written as 1 over 1 plus J F over FB. What's FB? Not 1 over 2 pi RC, 1 over 2 pi R over L. Sorry? Yeah, you can write it. Here, write it as, help me out. It's getting late, so forgive me. It's 1 over 2 pi L over R. What's the time constant for an RL circuit? L over R. So what happens is, yeah, it's 1 over 2 pi tau. If it's an RC circuit, it's RC. The only thing I have to show you now on Thursday, which I'm going to repeat this, is that it's 1 over 2 pi tau, but tau is L over R. Did I do that right? I'm feeling fatigued here. Did I get it right? Does that get it? So is it always RC? No. Sometimes it's L over R. Now, not that I think I would do this, Matt. We'll make this the final comment. I was going to show you a third problem. I've made a mental note not to ask you it, so I'm not even going to tell you what it is. This is it. Matt, the only other thing, and I don't know if I'm devious enough to do this. I think this would be devious before Thanksgiving, but it's not that hard. Matt, we had a capacitor, right? I don't think this is much of a trick. The break frequency is 1 over 2 pi REQC. And REQ is R1 plus R2. That's about as devious as I think I'm going to get. All right? All right. Before we break, how did we do? All right, did we achieve our goals? Andrew, thank you. You're the man. Thanks, Andrew. Thanks, everybody. Appreciate it. I'm going home to have dinner. Take care, everybody.